Okay, good evening everyone, and welcome to an episode of Physics Rocks It's True, and we are going to take a look at waves this evening. We're going to take a look at the basics of waves. So we're going to look at wave kind of types, we're going to look at wave equations, we're going to take a frequency, and we're going to do the basic questions that revolve around that. We're not going to take a look at reflection, refraction, or any of those things this evening. This is very much equation based. Now, if you're pretty strong on that already, I suggest you take a look in the description below. You will see a link to a set of questions that I've put together from past papers, along with the mark scheme connected to that. So if you want to stay on stream but actually work at those off to the side, then you can dip back in and dip back out as you require. Okay, just a quick check. Can I get a shout in chat? Is the microphone running okay? We're operating on a new mic this evening because of all the hate that I got in the last stream that I did. Okay, anyone that? Yep, we're all good. All right, cool. Okay, doke. Then let's get started. Then good job. All right. So let's get started. We're going to take a look at our two types of waves. Okay, so fundamentally we have two types of ways of making waves happen. If we take some form of disturbance system and we move an object in the upwards and kind of downwards direction, backwards and forwards, right? Then what I'm going to end up creating is a ripple pattern that looks sort of like this, without access to my own board. Okay, so this is pretty bad from a mouse, but you get this up-down feature going on all over that. Okay, an up-down feature. Now, the important thing here is that the wave is going in this kind of dotted line direction. The wave itself travels this way, so it starts off here and then it goes this way. Right? And because the wave and what is creating the wave, the disturbance that's creating it, are at right angles to each other. Okay, so we've got a little right angle going on here. I need a sketch pad beside my computer. Anyway, so we've got a little right angle going on here. Then this is a transverse wave. Okay, so transverse wave for this one. Transverse waves are very, very cool because you can make them in lots and lots of different ways. Like, and not only in the uppy downy direction here, but I could have a wave, I could have disturbances coming into and out of the screen. That would also be at right angles if you think kind of Z-axis in terms of when you're drawing X, Y, and Z axes in math. Okay, so this would be a Z-axis parameter, and it would still create a wave that goes this way. All right, so transverse waves are kind of cool that way. And when you get to do A-level physics, we'll talk to you about how that's a really useful thing, and we can do things called polarization with waves. But that's a teaser for next time. The only other way really that you can create a wave is by making a disturbance, this is one in green, that runs like kind of backwards and forwards like this, and that results in some form of compression system going on. So say we have a series of links kind of stuck together that you get, some of them get squashed and then they kind of end up partly spaced out a little bit later on. If anybody wants to invest in a gaming mouse pad for me, oh yeah, that would be amazing. So that I'm not working on this heap of crap desk that I have at the moment. So we've got kind of tight together and then a spaced out bit, group that together, and then just let's do a couple of repeats of that. Okay, so if I go backwards and forwards, what I end up getting is this kind of compressed, spread out system. All right. Now in this case, my wave is still going in the same direction as the transverse wave. It's progressing this way. Right. So in this one, my wave is parallel. The actual direction is parallel to the disturbance. And yeah, spelling was right there. And then this type of wave gets called a longitudinal wave. Okay. Longitudinal, longitudinal. Okay. Happy? And again, spell check is a bit slow on this one tonight. Okay, so transverse waves and longitudinal waves, those are your two types of waves. Longitudinal waves, only one way to make them, and that is there's only one line that's going to be parallel to the direction of travel of your wave. So unlike the transverse wave that you can make in millions of different ways, the longitudinal wave, only one way can be done for that one. Okay, so you're stuck with that. Okay, longitudinal waves and transverse waves, though, have in common the fact that they are waves. So we need to establish what a wave is. So that's a wave, and that's a type of wave. So what are waves? And waves do two things. Right? They transfer energy from point A to point B. Right? And that's kind of useful, but not any way different to like throwing a ball or flying a plane or moving a car or anything along those lines that transfers kinetic and potential energy and stuff like that. Okay, the key thing that waves do is they do it without any overall, and that I'm going to underline that because that's the key word there, overall movement of matter. And by matter I mean stuff, like things. Technically, scientifically, we're talking about atoms, molecules, particles, but it could be anything, like no overall movement of water, no overall movement of springs, no overall movement of air. It doesn't matter. There's no overall movement of matter. Now, clearly, when this is happening, this up-down wavy thing is happening, there's a crap ton of movement going on. But then once it passes, all the water goes back to where it was, but the energy travels onwards. When you're standing on the beach with the water licking around your legs and it's all like, oh, very tickly and lovely, you get an energy there, but it's not like the sea is coming up and continuing to travel onto the land. If you come back a little bit later, the sea is still back where it was. Happy? Alright, so establishing what waves are, they transfer energy from A to B without any overall movement of matter, and you got two types, transverse and longitudinal. Transverse waves, the disturbance here, I'm going to label this as disturbance. The thing that's causing it is at right angles to the direction of travel of the wave, and in this one our disturbance, you can label that, is parallel to the direction of travel of the wave. Okay, are we clear on that? I hope so. I hope so. So really what we want to move on to next is the diagrams that you get from this, because in exam situations you tend to be asked about graphs. Okay, now confusing point number one is that the graphs for longitudinal waves and transverse waves look exactly the same. That's not the confusing part. The confusing part is they look exactly the same and they look like transverse waves. That's the confusing part. Okay, but don't be confused. What you're not seeing pictures here. You are seeing descriptions of how things move over time. Okay, so this is let's start with a displacement graph. A displacement graph here. So we've got displacement up the side. I'll rotate that round if I can. Come on, play nice. Over here, and green button, rotate. There we go. So displacement up the side, and we're going to put displacement across the bottom as well. Okay, so first of all, you're going to go, right, okay, well, what's a displacement graph? That's a bit mental. Now we've got the same measurement twice. We don't. Okay, so let's take a look at let's go take a brand new page, and let's take a look at a really kind of simply drawn transverse wave. Transverse waves are probably the easiest to explain. So again, my apologies for the terrible wave I'm drawing here, but it is transverse. It's just not very good. Okay, so if I was to establish if I was taking a picture of a wave, okay, so this is an instant in time, because waves don't sit still, they move, but I take a photograph of this right now and I want to reproduce that on a graph, then I need to know where every single little point on this graph is. So I need a point here, I need to know where that point is, I need to know where that point is, I need to know where that point is, I need to know all the in-between points as well. I need a big table of results for this. Okay, so how would I know where they are? Well, what I'd do is I'd set up a grid system, because I'm a good physicist that way, and I would go, right, well, I need an x coordinate to there, and I'm going to need a y coordinate to there as well. Okay, so I need an x and a y. I need a displacement x and a displacement y, and that's what I'm seeing on this graph here. I'm seeing at a particular instant in time what is the displacement x and the displacement y from some rest position that I've arbitrarily set. Okay, from some start point here that's 0, 0. I have set this up. Okay, so up we go. Let's draw that in. Okay, so good cycle of a wave. Oh my goodness gracious me. I really should have had a pre-prepared graphic on this. I'm so sorry. This is live, you see. This was in the editing suite, would sort that out. But anyway, right, so what we've got here is we've got sort of a snapshot picture of our wave. Okay, so we need to be able to measure stuff from this, because that's why we bother drawing graphs. We want information. You don't bother drawing graphs if you don't want information from them. Okay, so you need to be able to interrogate this thing. So what can we get? We can get information here. Okay, so this point here, this zero line here along the bottom is special. This zero line is the rest position. So along x, this is the rest position of the wave. Now that's when the wave goes past, this is where all your particles are going to end up back at. They're going to end up back at this rest position, straight as if nothing ever happened. This point here up at the top represents the maximum displacement you can get away from rest. Okay, so this is the furthest away the graph gets from being at rest. Okay, as a result, because it's furthest away and in the positive direction, we call this a crest. On the other side here, at the furthest away position in the opposite direction, in the negative direction, we call this a trough. And if you had somebody who could actually draw, these two would be symmetrical to each other. Okay, so this distance here and this distance here would be exactly the same. Right? The distance that you are away from the rest position to a crest or to a trough is called the amplitude. The UDP, amplitude. So this is the amplitude of our wave. Okay, it's measured in meters because it's the displacement, or centimeters, or something else that's like this. Yes, yes, Cans, this is GCSE. Okay, down to the bottom is exactly the same. So the distance from my rest position down to my trough, which ideally should be the same, so sorry about the bad drawing, is also an amplitude. Okay, so that's an amplitude too. Which means that for those of you who are at least vaguely competent with maths, that the total height of my wave, so that little green line there from the trough all the way up to a crest, that total height is 2 times the amplitude. And that's a little handy one to know, because if I'm an examiner, I might set that as a little question, give you a picture of a wave, say the entire height of this wave is 10 meters, what's the amplitude? And you're expected to know that the amplitude is half the height of the wave. Alright, so but we'll not put that in our diagram because it's a little bit ugly looking, and we don't want too many lines going on. Now the real thing here, the real thing that we probably want information from, and we'll see why later on, is as a distance. We want to know how far it is from the crest of one wave over to the crest of the next one. Right? And I don't mean roughly, I mean the absolute pinnacle point of this wave to the absolute pinnacle point of this next wave. Okay, there's no mucking about in this in diagrams. It has to be right from the crest of one wave to the crest of the next wave, or from the trough of one wave to the trough of the next wave. If we had it, that would be the same. And this is the length of one wave. Okay, so a wave is the full time it takes to start off at rest, go all the way up, come all the way down, and go back up to rest. Okay, so that's a full cycle of a wave, which also happens to be the time it takes to get from the top down to the bottom and then back up to the top again. And the length that your wave covers in that time is handily known as the wave length, in a marvellous piece of physics being vaguely sensible for a change. Now we can't stay sensible for long, and we're going to give that a Greek symbol, and we give it the Greek symbol lambda, which looks a little bit like that. And that's the fancy version. If you're on a computer, in reality you end up drawing it as basically a triangle here with a hat and a line down like that. Okay, so you're kind of giraffe going to the left is what you're after. That'll do for lambda. It doesn't have to be some beautiful piece of work of art. Okay, happy? Good. Okay, so that's fun and that's interesting. That's a little bit of information that we can get from this. We'll do the equations for that in a moment, but this only tells us about our wave, you know, for 1 second, or not even a second, for an instant in time, just one snapshot. And I don't want that. I want to be able to describe what happens to this wave over a period of time, because that's what waves do. There tend to be loads of them coming one after the other, after the other, after the other, transferring energy in a kind of continuous way. So we want to sort that out. So go back to our little test page here, and we're going to look at this guy here, this little particle. Because as time goes on, this wave is going to keep traveling and is going to be replaced by other waves behind it, and it's going to go all the way through the system, and that little particle is going to be affected by that. So as the wave travels, as he makes a wave, this little particle is going to move all the way up. He's going to be a crest at some point, and then he's come crashing all the way down. He's going to be a trough at another point, and then he's going to go all the way back up and be a crest again, and all the way back down and be a trough again, and all the way up and all the way down and all the way up and all the way down. And you get the point. We could do this for a little while until the wave stops going on. Now if I was to draw the path of what that little wave is doing, it'd go down and then up and then down and then up and then down and then up and then down and then up in a completely non-interesting straight line. But if I was to plot that in a graph with time on the x-axis, this little up, down, up, down, up, down line would be stretched out, because I'd be moving down, up, but also to the right. Okay, so we back this up and let's make ourselves a different graph. I'm seeing a couple of my year 8s pop into the chat on this one, which is kind of cool. Folks, this is why we teach you graphs, because this is what you end up doing. So if I put displacement up the side, I'm still on symbol, so our Greek listener, our Greek watchers suddenly got really excited there, but no, this is displacement, the side, and we're going to rotate that round. Okay, again, so we've got displacement at the side. We're still looking at displacement, how far away our individual particle is from rest, but this time I want to see what happens to him over a period of time. And interestingly, the graph sort of looks the same, that as time goes on, our little particle goes all the way up, comes back down to his original position, then goes all the way down again, comes back up to his original position, goes all the way up again, and then goes back down again, in a much smoother way than has been shown by my rather erratic diagram there. But the point is, we can get information from this graph in the same way that we can get it from the other one. Again, we can see the maximum displacement from a rest position. And again, we have a crest, so we'll just copy that out of there. Again, we have a trough, and those measurements are going to be exactly the same if this is the same wave we're describing. So again, that's an amplitude, and so's this down here. And hopefully this graph's a little bit better for this one, but you know, we're getting the idea. Our zero line across the x-axis represents our rest position once more. The difference here now is the line from crest to crest. Okay? Because no longer are we looking at a length. Because if I was to measure this from a graph, this would be a certain number of seconds. And seconds is not a length. Obviously, lengths are meters, centimeters, inches if you're from America. I'm doing it wrong. It should be a unit of that type. This, on the other hand, is a time. So this is the wave time, and it should be measured in seconds. Now, we don't call the wave time because that would be far too sensible. It is the time taken for a full cycle of the wave, and we call that the period of the wave. Okay, so for those of you who have who like attend school, that's most of the people that's in here. If you're attending class, you have period 1, period 2, period 3, period 4, and that is a certain amount of time. It's normally a set time in which the cycle starts again. Okay, so in our place, 35 minutes, 30 minutes, or whatever. So the time it takes from crest to crest is called the period, and it gets a special symbol. Instead of getting lambda, it gets big T. Okay, normally little t is used for time. Okay, so this is an important time. So big T. All good? Nice one. Hey, so popping on now. Just had a quick look at chat. It's surprisingly not terrible for a change. So on we go. We're going to take a look now at the equations that come from this. So in waves, we have this kind of main concept, which is frequency. If you're going to talk about waves, you're going to need to understand frequency. And the frequency of anything is the number of times an event happens in a given period of time. Now, that's true for life. That's an English definition. It's not a physics definition. You know, if something happens frequently, it happens loads and loads and loads and loads and loads in a given period of time, and something that happens infrequently, it happens very rarely in that same period of time. Okay, Christmas happens, you know, if you're young, it happens far too irregularly, once a year. All right. If, however, you know, going to school happens every day, that's maybe a little bit too frequently, and the number of times you come to my physics class happens, you know, between 2 and 3 times a week, which is certainly not frequently enough. Okay, so frequency is the number of times an event happens in a given period of time. Now, expressing that mathematically is the important bit. That frequency, f, is equal to the number of times the event happens, we're going to call that n, divided by the time it takes that you're actually measuring those events to happen, t. So we've got a fractional relationship here. Okay, so f is equal to n over t. Right. The gaming videos from chat there, they'll happen when I get a machine that can actually handle a gaming video. If you want to see, you know, 2 frames a second me playing Counter-Strike Source, like we can make that happen. But anyway, right, on we go. So frequency equals n over t. Frequency, number of events divided by the time taken. Now that is true for all waves. And if you're going to learn one equation for frequency, learn this one. There is a very special case of this one though, which is that if the number of events is equal to 1, so if n equals 1, okay, that means you get one wave in the whole time. One complete wave, not 1.02, not 0.85, one, bang on one, 1.0 recurring to infinity. Am I making myself clear? One, not even close to one, just one, exactly. That this is then the frequency is equal to, instead of n, we have the actual number, 1, divided by the time it takes for one wave, which we've just established in the previous one as being the period, 1 over t. So if you are given the frequency, or if you're given the period, you can find the frequency by using frequency is 1 over the period. For those of you who hate maths, that shouldn't be anybody. Math is awesome and you should love it. You can rearrange this equation pretty quickly and pretty handily to being, therefore, the period is equal to 1 over the frequency. So if you know the frequency of something, you know the time it takes for a single wave just by popping that into that equation there. Right, so the next time that you're tuning in your radio to a certain number of kilohertz, you can actually work out how many seconds it should take for that wave. Now, important things here, we're doing physics, so therefore we need to be careful on our units. Right, so in this one, we have frequency here and we have time period here. These need to be in the right units. So frequency is measured in hertz, Hz. Okay, so H-E-R-T-Z, hertz. And the time period t has to be measured in seconds. Okay, and I'll put that in as s because that's how I did the first one. So s in seconds, little s for seconds. Once you've got that right, you're in business. Okay, so standard exam question is something like, 10 waves pass a point in 40 seconds. And you just pop in 10 over 40 into your calculator, 0.25. Done. Alright? Happy? Okay, yeah, that's a fair point, actually. But bless him, he's trying his best there to chat about communism in a physics stream, which I think you may have found the wrong place. I think you've mistaken physics with politics, mate. But that's all right. You might learn something here. Okay, so frequency is n over t. Now, the next equation that we need to know is the wave equation. Now, if I had more than about 7 minutes to explain this to you, I would explain to you that the wave equation is nothing more than a rearrangement of speed equals distance over time. And we might even try that. If I want to define my wave speed, instead of using s because there's seconds and stuff going on here, we're going to use v, our standard thing for velocity. And that's going to equal the distance that my wave travels, right? So well, that could be anything. But there are certain distances that I'm more likely to know than others. So the distance it travels, let's think the distance it travels for a single wave is going to be lambda, the wavelength. So how long is a particular wave? And we're going to divide that by the time it takes, because speed is equal to distance divided by time. So if one wave travels lambda, how long does it take to do that? Well, it takes one period to travel one wavelength. So that is lambda over t. Now notice that I haven't done anything special, I've just put our new symbols into speed equals distance over time. And I've got myself a speed equals distance over time equation that relates only to waves, that v is equal to lambda over big T. Right. Popping that onwards then, we can do a little bit of jiggery pokery with maths and find that therefore v is equal to lambda multiplied by, this is a bit annoying getting fractions in here, but we're getting there, multiplied by 1 over t. Now shout in the comments or in the bits at the side that if you understand that or not. Okay, so in the chat, are we okay with that? That dividing something by t is exactly the same as multiplying it by 1 over t. Is that alright? Yes? No? Happy? No t? Well, no t, you're yeah, of course. Ben, you're good in that. Excellent. Nice one. Nice one. Alright, for the first years actually you should be okay with this. This is an inverse operation, that multiplying is the same as dividing, just the other way round. Okay, so instead of dividing by t, we're multiplying by a fraction over t. Right. Now that's only interesting because we can change 1 over t into f, which gives us our final equation and the equation that you want to take into the exam with you, which is the v equals lambda f. Or more usually written as f lambda because we put the Greek at the end just for fun. Okay, so v equals f lambda. And that gives us v is the wave speed in meters per second, f is the frequency in hertz, and lambda is the wavelength in meters. And these all need to be right. These all need to be absolutely spot on. Now, what we can do a little bit of is, this is in meters per second. Okay, this is in hertz, and therefore this has to be in meters, otherwise you wouldn't get a distance in meters per second. Now you can be quite clever about this. If you want to go a little bit extra, you could, if you had this in centimeters, leave it in centimeters. You've got no choice but to have this in hertz. This has to be in hertz, no choice about it. Watch for things like kilohertz, because you need to change that into thousands of hertz. But you know, that has to be in hertz. But if this was in centimeters and that was in hertz, this would give you a speed in centimeters per second, because hertz is really just 1 over seconds. And this is the equation that you absolutely need to go into. You're going into a GCSE exam, you will be examined on this equation. It will appear. There's absolutely no way it's not going to appear. So you know, just make sure you know this one. Okay, happy? Don't you have something better to do? I'm hoping you're not talking to me. I hope you're talking to somebody else. But cool. All right, happy? Oh, so wait, sir, can you repeat the fact about the two things that mean the same thing? So this thing here, the lambda over t and the lambda times 1 over t, is that what we're after? Okay, Ashton, is that what you're after on that one? So if I divide by t, okay, so think about if I divide something by 2, that's the same as multiplying by a half, isn't it? If I divide by 3, it's the same as multiplying by a third. So if I divide by t, it's the same as multiplying by a teeth. A teeth, that sounds bad, but 1 over t. Okay, so dividing by 6 is the same as multiplying by 1 over 6. Dividing by 10 is the same as multiplying by 1 over 10. Therefore, dividing by t has to be the same as multiplying by 1 over t. And then since 1 over t, so this bit here is actually this equation, whoop, wrong way round arrow, is actually this equation up here. That 1 over t bit gets replaced with f. Okay. Is that okay? All right, cool. I'm hoping this is better. Okay, get it. Nice one. Nice one. Good. Thanks for interacting in chat. That's brilliant. And this kind of leads us to the end of our equations on this. All right, so the only thing I want to talk to you now about is real life situations with waves. So this will take 2 minutes to finish us off, which is about all we've got left in the stream. I'll maybe talk a little bit beyond that. If you've got stuff to do, I understand if you have to go. I did say half an hour. But in real life, if you make a wave and you just let it go, what tends to happen is if you're looking at that one little particle, your wave tends to go like this. That it starts off really big, but then over time, energy gets lost. Okay, and it comes down, it comes down, it comes down. And the amplitude of your wave gets less and less and less. Because the amplitude of your wave is a pretty good indication of its energy. If this was a sound wave, for example, the amplitude would indicate its loudness. Right, so over time, this is going to come down. The frequency of my wave is simply related to how far apart these little peaks are. And provided these peaks remain the same distance apart, which is, I really tried to do that for the first two and really failed badly at the last ones. Provided these gaps kind of work and are the same distance apart, then the frequency is the same. So frequency, Q-U-E-N-C-Y, F-R-E-Q-U-E-N, is the same if the crest to crest time remains constant. And for most things that's true. Like if you make a sound, if I shout, it stays at pretty much the same frequency as it travels. It gets quieter and quieter and quieter, but people at the back of the room don't hear me like much more manly and much more deep pitched. And the people at the front don't hear me in a really high key, sweetie voice. It's pretty much the same thing, just quieter at the back. All right? Happy with that one. Whereas as the amplitude dies, so amplitude, so this is if we're simply talking about sound waves, amplitude is kind of related to loudness, and it will then decrease over time. So the frequency is set by whatever makes it and tends to stay constant. The amplitude runs down. Now there are exceptions. Frequency does change, right? I don't want a whole pile of hate afterwards where people have looked up, like obviously it does change, but for most situations it doesn't really. For most real life situations, the amplitude is going to die away long before the frequency does. Okay, any form of frequency change is going to happen. And this is important, especially in the waves questions that I've set as the additional work for this, which is that if you drop down into the description below, if you just joined late, in the description below you'll see a link to a Google Doc. It is some CA past papers, set on this stuff from this video to see how you get on. There's a couple of questions that say, like, what's happening in this one? What's the difference in these two waves? What's similar about these waves? And as you see the amplitude drop off, you simply say, the amplitude dies as the wave goes on. But if the wave continues to have the same frequency as it goes on, or the same gaps here, the same distance from crest to crest to crest to crest, you can comfortably say that the frequency remains constant. All right? Okay, folks, that is 9 o'clock on the button by my mark. That's half hour of fun and physics for the evening. I want to thank all 24 of you in channel at the moment for turning up. I really appreciate it. If you enjoy the video, you know what to do. The lovely little thumbs up button that turns blue apparently if you press it. If you didn't like it, feel free to press the thumbs down button. Would you please leave a comment at the bottom? I'm new to this and I know I suck at it, but I want to get better at it because I think this is a good way of people being able to just grab half an hour's worth of revision that is pretty relaxed. Okay, if this is part of your revision schedule for the evening and you've got 17 minutes, which is the rated time on the work below, do take a copy of the work below it. It has a little mark scheme at the back of it. It's got a little mark thing. It's all set up to look exactly like a GCSE exam to give you that authentic feel to it. Okay, but for me, on this one, thank you so much for tuning in, everybody, and I will see you at school tomorrow. Okay, see you later.